In this part, we finally get to the derivation of the kinematic bicycle model, which is one of the central models in vehicle dynamics and control. So the kinematic bicycle model is a simplification of the kinematic four-wheel model that was covered in the previous video. The main idea is that the two rear wheels and the two front wheels are lumped together into one imaginary rear wheel and one imaginary front wheel respectively. So if we consider again our kinematic four-wheel model in white here, with O being the instantaneous center of rotation and the wheel orientations of the four wheels being shown in green, then we lump together the two rear wheels into one imaginary rear wheel right in the middle between the left and the right rear wheel, and same with the front wheels. So we lump together the left and the right front wheel into one imaginary wheel in the middle between the two. And then we connect these two wheels, and this forms our kinematic bicycle model in blue. Observe that with the kinematic assumption, namely that the slip angle of all wheels is 0, the kinematic bicycle model will behave exactly as the four-wheel kinematic model, because at each point in time it will have exactly the same instantaneous center of rotation as the four-wheel model. However, one big advantage of the kinematic bicycle model over the four-wheel model is that now we only have one front wheel and hence only one front wheel steering angle, whereas the four-wheel model has two steering angles for the two front wheels. Next, let's derive the equations of motion for the kinematic bicycle model. Here's a little sketch of our kinematic bicycle model in blue, with the instantaneous center of rotation in red, and we have chosen a reference point C on the kinematic bicycle model, and we call LF the distance between C and the front wheel, and LR the distance between C and the rear wheel. Obviously, we have LF plus LR is equal to L, the wheelbase. The model has a single steering angle, namely that of the front wheel, which is called delta, and it's defined as the difference between the kinematic bicycle's heading angle and the heading angle of the front wheel. By the fact that the kinematic bicycle model at this time instance is rotating around the point O, we have that the velocity vectors at the rear wheel and at the front wheel are perpendicular to the connection to O. And also we can draw the line between O and the reference point C, and then the velocity vector at the reference point, so the vehicle velocity by definition, is perpendicular to the line OC. Next, the vehicle's side slip angle, or just slip angle, is defined as the angle beta between the heading of the vehicle and the velocity vector v. Observe that the side slip angle depends on our choice of the reference point C. So in particular, if we choose C at the very front of the vehicle here, in other words, where LR is equal to L and LF is equal to 0, then the side slip angle is exactly equal to the steering angle delta. On the other hand, if we choose the reference point at the middle of the rear axle, back here, where LR is 0 and LF is equal to the wheelbase, then we would always get a side slip angle beta equal to 0. Note that here we assume the vehicle is moving in a horizontal plane, so we may describe the position of the vehicle by the inertial coordinates x and y. The orientation of the vehicle is described entirely by its yaw angle psi. The goal is now to obtain a set of differential equations that describe the motion of the vehicle, meaning the evolution of the coordinates x and y over time t, and the evolution of the yaw angle psi over time t. First, let's look at this by assuming a constant absolute value of the velocity. In this case, the incremental change of the coordinate x and y amounts to the corresponding components of the velocity vector v in the x and y direction, and the x component is given by v times the cosine of psi plus beta, where psi plus beta is the angle between the velocity vector v and the x-axis. And correspondingly, the y component of the velocity is given by v times the sine of psi plus beta. Moreover, by the fact that the kinematic bicycle model is rotating about the point O at this time instant, we can state that the change in the yaw angle psi dot is equal to the angular velocity of the rotation around the point O, which we call here omega. Since omega is the angular velocity of the reference point C around O, we can express omega simply with the Euler formula of v divided by r, where r is the radius of the rotation, meaning the distance from O to C. Now, the set of differential equations that describe the evolution of our vehicle coordinates x, y, and psi is almost complete, except that we need to find expressions for the sideslip angle beta and the radius r. To do this, we have to use a little bit of geometry. So first of all, let's call the distance from O to the center point of the real wheel by r bar. And then second, observe that the steering angle delta appears again here, and the sideslip angle beta appears again here. To see this, note that this angle here is 90 degrees, and hence this angle has to be 90 degrees minus delta. Now, if you look at this triangle, this angle here is 90 degrees. This angle is 90 degrees minus delta, so this angle up here has to be equal to delta. And the same argument works for the angle beta. So this angle here is beta, this angle is 90 degrees, so this angle is 90 degrees minus beta. Now we look at this triangle, and we note that here we have 90 degrees, here we have 90 degrees minus beta, so this angle has to be equal to beta. Now we just apply some basic trigonometry. First of all, looking at the big triangle, this one here, where the tangent of delta is clearly equal to this length here, which is LF plus LR, divided by this length, which is equal to R bar. So that solving for R bar yields the expression LF plus LR divided by the tangent of delta. Using the same idea in this smaller triangle, we get that the tangent of beta is equal to this length, so LR, divided by this length, which is R bar. But we have just found an expression for R bar, so we may substitute this expression into the tangent of beta, and by this we obtain the tangent of beta equal to LR divided by LF plus LR times the tangent of the steering angle delta. So by taking the atan of both sides, we have found an explicit expression for the sideslip angle beta in terms of variables of the kinematic bicycle model. Now let's do the same thing for the radius r. And to do this, let's look again at the small triangle, this one, and realize that the cosine of beta is given as the fraction between r bar and r. Since we've already found expressions for beta and also r bar, we may simply solve this formula for the value of 1 over r. And we need 1 over r in this formula here. That's why we solve for 1 over r. And what we get is that 1 over r equals to 1 over r bar times cosine beta. And now we can just substitute the expression for r bar from up here, and we get that 1 over r is equal to 1 over LF plus LR times tangent of delta times the cosine of beta. In summary, we have obtained the equations of motion for the kinematic bicycle model by 3 nonlinear differential equations for the 3 states of the vehicle, namely x, y, and psi. And there's one input to that model, namely the steering angle delta, and the side slip angle beta is just given by a static trigonometric transformation of the steering angle delta, which depends on the location of the vehicle reference point. One final remark about the assumption of a constant velocity v. So in many cases, this v here is actually made a second input of the kinematic bicycle model, or we may want to add a fourth differential equation to the vehicle model where v dot is given as the acceleration a, and a is an external input to the model that can be freely chosen.